method we have been seeing last week. So just let me briefly remind what we had seen. We have take as a reference the even nuclei and produce through RPA or through the vibrating potential model are simply two methods. We have produces the phonons, which are many for each multipolarity. And for the odd, we add a particle. And of course, the core can still perform excitations of phononic type, so we will also have configurations of this kind, eventually with two phonons, three phonons, also here, of course. And we were dealing mainly with the interaction between the basic elements, namely the particle and the phonon, through the so-called particle vibration coupling vertex that sometimes we call H, between particle and a particle phonon. Remember that we have four different possibilities of the similar type: the Hall scattering, the vacuum polarization, and the Hall decay. Okay. And with these elements, we can construct a whole spectra with energies Ej, be Ej the energy of the particle, h bar omega, 2h bar omega, 3h bar omega, the number of phonons we put. And this would be quite of degenerate, because here you can have a lot of possibilities for the angular momenta. This is for the odd nucleus. For the even nucleus, we will have also degenerate, because the total number for the angular momentum can go from n lambda and below. But all these strong degenerations breaks through the interaction by means of the basic vertices here. So breaking off degeneracy by diagonalizing or treating perturbatively the particle vibration coupling. So this is the scheme, and I present to you last day an application to the septuplet in bismuth 209 by Ikuko. It's a classical work. And we saw that the main features of the splitting of this multiplet, which was, well, maybe I can show you again. Well, you have seen it already. We saw that the main features were reproduced by the particle vibration coupling. Okay, let me underline why I presented this as a first application. And the fact is that this breaking of degeneracy in a multiplet, in general, in any multiplet, is 100% due to the, per definition, the coupling between the particle and the phonon. If you don't have any interaction between the particle and the phonon, per definition, by definition, you would have degeneracy. So if you have a nucleus and you can look at any of the many multiplets that can be produced, you will be getting a neat signature of how strong the particle vibration coupling in this nucleus is. So, in some sense, the particle vibration coupling, as maybe Galileo would say, is written in the book of nature. You just go to the data and you analyze this splitting. You are reading how much the particle vibration coupling is. And even more, it's very much model independent. We have been always saying that the first thing we have to do is to produce a Hartree Fock or to generate some Booth-Saxon single particle levels. But if you analyze precisely the splitting, nothing more than the splitting, not the position of the multiplet, but just the splitting, it depends extremely little on the details of the Hartree Fock. And even more, if you just take the phonon, the experimental phonon properties, namely the frequency and the electromagnetic transition strength, then you just go to the splitting of the multiplet, and you get from there the strength of this basic mechanism. But let me show you today another application before we proceed to a superfluid system that merit to be at least remember, which is wow. Okay, which is the other application we saw, namely the self-energy. That is the shift, the modification in energy due to the particle vibration coupling. And this is also a classical work by Bortignon, Broglie, Dasso, and Mao, where they started by using some Scherm set of levels, in this case related to lead 208. So, thank you. Related to lead 208. It was it's an old application, so it's also an old Scherm interaction. And the levels you get are these ones. Experimentally, the main single particle strength is at energies that you can see here. And as I was saying last week, a usual feature of the Hartree Fock is to give a too large spacing, or if you want, a too low density level around the Fermi energy. The Fermi energy would be something like here. And you see here, as a rule, what I told you last day, that the particle states, after you add these two corrections, tend to approach the Fermi energy, so the particles go a little bit down, and the whole states go a little bit up. And then, in this way, you obtain better agreement with data. And this is okay. But in this case, your comparison with the data depends, of course, very clearly, on the starting point. If you start with another set of single particle levels, maybe the agreement wouldn't be so nice, or would be even better. So there is something that is in some way out of the particle vibration coupling let's say responsibility, which is the Hartree Fock that you start with. There are some Hartree Fock parametrizations, in particular some Scherm parametrizations, that at the simple level of Hartree Fock already gave a level density close to the experimental one, so leaving no room to the particle vibration coupling. Well, but today, as I told you, I would like to present more recent applications, and in particular, I will present applications concerning concerning 1,120. 1,120 is a so-called superfluid nucleus It's an even nucleus, of course, but it's not a closed shell, not even a shell closed nucleus. Here you can see the levels around the Fermi energy. Fermi energy for T120 is about here. And one could think, well, this would be a kind of closed shell where this maybe probably, yeah. One could think that maybe just filling, in principle, these subshells here, you would be okay. But the fact is that this energy gap is little. It's about 1 MeV or little, or something similar. And nucleons like to profit from the possibility of jumping here strongly. Remember that we were saying that in the ground state we can have two particle to holes configurations. But if the gap is small enough, it happens that this occupancy becomes very, very, let's say, distributed. And it is well described by the BCS equation. I don't know if you have already seen some of this stuff, okay? So this is the thing that happens in 120. You have a superfluid situation in which the occupation of the levels is smooth, changing around the Fermi energy. And in this case, well, you have to solve not the Hartree-Fock, but the Hartree-Fock-Bogoliubov equation. Or more simply, the BCS equation. The BCS equation is a simplification of it's the original equation, but it's a simple version, one could say, of the more sophisticated Hartree-Fock-Bogoliubov. If you write down the Hartree-Fock-Bogoliubov in the BCS approximation, you can write it in this way. This is the energy referred to the Fermi energy, the pairing gap, and here you have the large and the small components of the quasi-particles that then, through the Bogoliubov transformation, gives you the occupation numbers in the superfluid phase, where, well, you have to consider that before the BCS, you had levels above the Fermi energy or below the Fermi energy, namely U0 and V0 were 1, 0, or the other way around, 0, 1 for the levels below. And this BCS equation has to be solved self-consistently because the pairing gap is something that depends in the BCS equation and also in the Hartree-Fock-Bogoliubov on the occupation numbers that you obtain from the equation through the Bogoliubov transformation. So these equations have to be solved consistently, and this is something similar to what you do with Hartree-Fock. Also Hartree-Fock have to be solved consistently. In the case of BCS, you have something similar, but concerning the pairing field, the pairing gap. Okay, so in this pairing gap, a very important ingredient is the so-called pairing matrix element, the interaction that makes particles couple in the superfluid phase. They couple through the pairing interaction, giving rise to what is called Cooper pairs. So if you have two neutrons that belong to the superfluid phase, they interact through the pairing interaction. They couple to 0. So the BCS, usually the matrix element that is of relevance is the one in which you go from coupled to 0 to similar or equal angular momentum to two other different ones. This is what we can call GJ prime J. Okay, this is a basic ingredient. A basic ingredient is the one giving rise to the superfluidity in the in this case in 120. Okay, in principle, well, this interaction should be provided by the nucleon-nucleon interaction. But remind, for example, where was discovered the superfluidity. Superfluidity and superconductivity was discovered in solid state, superconductivity, and there, after some time, they realized that the interaction between electrons, which in principle is repulsive, instead for generating something, some condensed object as the Cooper pair, you need an attractive interaction. Why? This is the reason why you need a negative matrix element. So if you want to get a superfluid situation, this has to be negative. That is, has to be related with an attractive interaction. But in solid state, this was a problem because electrons in principle get repulsive interaction. But, well, as you probably know well, this was solved by the mechanisms of phonon exchange. These were lattice phonons. And this interaction, if you evaluate it following the rules we have seen the other day, this is a similar, these are two equal essentially vertices, and the denominator is negative because you have the denominator of the starting state in two time reversed orbits, and in the intermediate state you have also two electron states plus the energy of the phonon. Well, this is very much negative as a rule, at least where you are when the electrons and the electron energies are close to the Fermi energy, and this was the basis for explaining superconductivity, in solid state. Well, in nuclei we have similar, very, very similar situation. Well, proton-proton or neutron-neutron is attractive. This already can give some pairing interaction, of course. It's not like in the case of electrons because of the strong force. But nevertheless, we still have phonons. We still have phonons, and they, of course, can play the same role, and by the same arguments, you get that this is an attractive interaction. In fact, before than any calculation were done, in the classic book of nuclear structure by Bora Mottelson, one finds a very little paragraph commenting on this possibility. was no more than what you can see here, these few lines, where they were discussing this possibility and concluded in the last sentence that this interaction, that they call polarization interaction, resulting from the coupling to low frequency modes, maybe could be even larger than the bare force, for some reasons that were discussed there. Well, several years later, we tried, just using the partition coupling, to look at these matrix elements, pairing matrix elements. They are calculated, as I have already told you, the vertex square, the energy difference with respect to the intermediate state, and with this pair interaction, and nothing else, just to check what happens with no direct nucleon-nucleon interaction, just this polarization, we solved the pairing gap equation, which in this case is written in this way. And what we got for the case of 120 is shown here. Here we show many levels, neutron levels in particular, of the 120. They are ordered in energy. So the few levels I showed you before are these ones, maybe this one. But in this case, the calculation was extended further away, just to check what happened to far away single particle levels. And here we plot the pairing gap that we obtained for each different single particle state. And, well, you can see that the numbers we were getting around the Fermi energy are of the order of 1 MeV. And if you take into account that the experimental pairing gap deduced from the odd-even mass staggering in the binding energies is about 1.4. So you see that a sizable portion of the experimental number could be, or of course, could have some contribution from this mechanism here. But, well, this was interesting, but of course, one cannot forget that the nucleon-nucleon interaction is there. So in principle, one has to proceed to the inclusion of both in the pairing gap. One should take the nucleon-nucleon interaction plus the interaction due to the phonon exchange between nucleons. This, by the way, is usually called induced interaction, induced pairing interaction. Okay, and if you put both of them, just by adding the numbers and substitute in the pairing gap equation, in the BCS, well, you obtain an extremely large number. It's something maybe 3 MeV, or it depends on how you exactly did the things. But you obtain a gap, summing bare plus induced interactions, which is sizably larger than the experimental one. Well, the reason for this is that this way of proceeding is too simple. Is too simple. Because, okay, we know, or we can believe, that we have particle vibration coupling between different states, giving rise to the induced pair interaction. But we know from the lessons we had the last week, that together with these processes, we have the self-energy processes. I mean, one cannot forget when studying a process that many other processes are going on in the nucleus. And in particular, this self-energy renormalization of the single particle states. Well, as we will see just now, these processes that, if you remember, were described in the last lecture, or in the last time we were together, can be described in this way. Remember that this is the matricial form of the self-energy corrections. The self-energy correction, if you want, can be obtained by performing the perturbation treatment of this matrix in the usual way, by multiplying the perturbation and dividing by the difference in energy, or you can proceed to diagonalize the matrix. Remember that these matrix elements, the one associated to the first component, was related to the first single process. The other amplitude with this other denominator was related to the second one. And we were able, in the last minute of the last lesson, to include simultaneously in the same equation the renormalization of particles and the renormalization of holes with the same angular momentum, meaning that the particle and the hole can couple to the same configuration of particle phonons. And we were able to produce this matrix. In this case, I have already introduced it in the diagonal, the Fermi energy that we didn't have the other day. Of course, if you subtract the Fermi energy in the diagonal, you subtract it also from the eigenvalue. This is no problem. And even more, in the case of hole configurations, where this difference would be negative, I have written here as the negative of the absolute value of the difference. So in this way, our particle vibration coupling matrix acquires a structure that is identical to the BCS. Well, it's here. This is the BCS, where you have the absolute values of the difference with respect to Fermi energy, the large and the small amplitudes, the eigenvalue, the pairing gap, and in our partition coupling, you have exactly the same structure, but with a 0 here and a 0 here. This is precisely the place where the pairing gap goes, the pairing gap due to the Bayer interaction in the BCS calculation. So you can see that it's extremely straightforward to incorporate both mechanisms, namely the BCS mechanism and the particle vibration mechanism, by simply including here the pairing field, as in fact it is done in the next equation. The only thing that we have to take care is that when you solve the BCS in a superfluid system, particles are simultaneously single particle states are simultaneously particle states and whole states. So you have to make a systematic doubling of the configurations. You cannot say anymore that this is a particle hole and this is, a particle phonon and this is a whole phonon. You have to take into account that this is partially a particle phonon and partially a whole phonon. And in the same way, here we have the sector for holes. You cannot say anymore that this is for sure a whole phonon, but it could be, to some extent, a particle phonon configuration. So you have to double the the possible configuration to which our particles can couple. But for the rest, the structure is exactly the same. For example, if you put to zero all the particle coupling, you recover immediately the BCS equation. Or if you eliminate the pairing gap in such a way that particle and holes are well defined, you recover immediately the particulation problem that we had the other day. So this is a plausible scheme for treating together pairing and particulation coupling in a consistent way. Well, this I have just shown to you is kind of plausibility argument, but this equation, exactly this equation, can be deduced from a completely analytical and mathematical procedure from the generalization of the particulation coupling to superfluid system. And I will give you in the end the references where you can find this let's say demonstration. Okay, this is a matrix that well, here is a 6 by 6, but remember this is the block now of particle whole character of whole particle phonon character. This is the block of whole phonon character. And from there we obtain many amplitudes. And these amplitudes have different meanings. The first amplitude, as we have seen every time we talk about particulation coupling, is related to the component in the original particle, so it's the so-called single particle amplitude. The other ones give you how much of the quasi-particle is constructed on top of this configuration, and the same for the other one. And these other are related to the backward amplitude of the phonons that appears through the whole phonon configuration. Well, and finally, we have here the epsilons. The epsilons now have to be interpreted exactly the same way as in BCS. They are playing exactly the same role, and these are giving us the small amplitude of the superfluid quasi-particle. Okay? Well, performing the Bogoliubov transformation that we saw before, the matrix elements for particulation coupling can be calculated from the ones that we already know, but now taking into account that the particle phonon or the whole phonon configurations are not pure, are partially particle phonon and partially whole phonon. So you have to take into account how much unoccupied or how much occupied they are in the solution of the problem. This equation, in principle, must be solved consistently as the BCS, because the UV factors appears not only in the gap equation as before, this has not changed, but also in the matrix elements. In the matrix elements appearing in the particulation coupling, how much something is a particle or how much something is a whole is decided by the U and V BCS amplitudes, and this, through the Bogoliubov transformation, is decided by the large and small amplitudes. So everything should be solved consistently, and well, this is kind of a problem because every time you diagonalize, you obtain a large number of solutions, not only one quasi-particle. You obtain only one quasi-particle if you solve just the BCS or the Hartree-Fock-Bogoliubov equation. But if you solve the particulation coupling, you obtain a large number of solutions. This, at least, you obtain as many solutions as the size of your matrix, or something of that order for sure. So every time you diagonalize, you produce a new states, J prime, J2 prime, to which your particle can couple. And if you solve iteratively, in the end, this number of states multiplies at every iteration. And the matrix would be larger and larger as you iterate. Well, there are several ways of treating this problem. One is to avoid it completely, namely to solve the BCS equation previously, and then on the basis of the quasi-particle states of the BCS, you solve the rest of the particle vibration coupling matrix elements. And this is something that has been done in literature. We have also checked. And but there are other methods in which you use green function methods or some other kind of mathematical equivalent procedures that now we have to just mention here. Okay, and finally, this equation, this large equation of 6 by 6, can be put in a compact way through the method by Bloch-Horowitz, and just projecting on the quasi-particle components, the large and the small quasi-particle components. So that finally we ended up with a BCS-like equation in which the off-diagonal is constructed in this way through the Baire interaction and through the phonon exchange. Here you have the phonon exchange part and the Baire interaction contribution. And finally, with a rather simple, but I will skip this, we arrive to the so-called generalized gap equation. Okay, which is a BCS-like equation, but in which you have the induced interaction, the Baire interaction, and some correcting factors that are due to these processes here. And in one so-called zeta factor, which has to do precisely with the self-energy processes written down here. Okay, with these elements, we can now see what is obtained in the case of 120. In this calculation, I will show you, I'm mainly using this scheme interaction. We had also tried to see what happens with this other, but the results belong mainly to this. And for the phonons, we have been using almost experimental data, namely the energies and the 0-point fluctuation. And the beta value, maybe I didn't say that before, is nothing but the 0-point fluctuation of the alpha multiplied by 2 lambda plus 1 square. It's just a kind of usual way of writing the 0-point fluctuation. So these are the basic elements of our calculation. Remember, we just need single particle states and phonon properties. And from there, everything comes out. And, for example, here you have what happens if we did only Hartree-Fock-Bogoliubov, and what happens if we add the processes of induced interaction and single particle self-energy. And we obtain a much compressed single particle spectra. In this case is quasi-particle spectra, which is in good agreement with experiment. But remember what I told in the beginning today, that the level density depends on what you start from. And in this case, it's a good starting point because we are ending something close to experiment. The pairing gap. The pairing gap is a quite, in a way, theoretical object, but also has some experimental counterpart from the even mass staggering. And as I told you, in the case of 120, it's about 1.4. If you just used the bare interaction, in this case, the argon interaction, it's a realistic interaction, you would obtain the black dots, which is, well, not very far from the experiment. But when you perform the whole calculation, now the contribution of the bare interaction, the argon interaction, is smaller. It's smaller because it must be corrected by the zeta function. This function has to do with the fragmentation of the levels. And of course, you get some contribution from the induced interaction, the phonon exchange interaction. And the sum of two gives you the final result. And in this case, I just compare what happens if I make a full iteration calculation or just a one iteration process. As I told you, the difference is not enormous, but the converge, when you really iterate, you obtain this one. So the experimental gap, which is not far from the final result, is, say, 50-50 coming in this calculation from the bare interaction and the phonon exchange interaction. Well, as I told you before, when you diagonalize the matrix, you not only obtain one quasi-particle, as in BCS, you obtain fragmentation. Namely, in BCS, you would obtain, with the same value of the quasi-particle energy, a particle amplitude or a whole amplitude for a given orbital, in this case, h11.5. See what we obtain when we diagonalize. This is the quasi-particle energy. In the case of BCS, you would obtain only one peak, only one quasi-particle energy. It's a usual way of, it's just an usual way of showing the particle amplitude and the whole amplitude. The one refers to 121 and the other to 100. Exactly. Yeah, this gives you the probability of, or the possibility of putting a particle on top of 120 and creating 121, or the possibility of extracting a particle from this orbital and producing 119 thing. And with only one quasi-particle energy, because BCS gives you only one quasi-particle. And the sum of these two peaks would be 1. 1 because gives you exactly the summation of both gives you the total single particle strength. Instead, when you diagonalize the more general matrix, you obtain many other solutions. This is an example where most of the strength, I mean, what you expect to see in the experiment, is concentrated precisely in only two peaks. But these peaks are not necessarily summing 1. When you sum this probability and this, you don't obtain 1 because you still have some fragments in this side and some fragments in this side at different energies. You obtain several eigenvalue and several strengths for producing 121 or 129. But in this case, in this particular case, for this orbital, what we expect is that experimentally we will observe mainly only two peaks. And in fact, this is what happens. How can we see this experimentally? Well, through the one-particle transfer. If you send a deuterium to 120 and you observe a proton, you know that a neutron has gone into the 120. So you are populating 121. And from the angular distribution of the proton, you can say which is the angular momentum you have been populating. And from the absolute cross-section, you know the probability with which this process is happening. So it's giving you this so-called spectroscopic factor. In this case, in this experiment, because of the experimental situation, they were not able to disentangle in the detectors the population of these two states in 121. But making an analysis, a theoretical analysis, you can disentangle both components. Okay, so in any case, some experimental value is got. Here you see the population of other different states, the 1/2 plus, and the 3/2 plus, and the 5/2 plus. All these dots are data, and all the lines are calculation done by DWBA, and using the spectroscopic factors we have obtained from this calculation. So you see that an overall description is obtained. But let me elaborate a little bit more on the case of a special, peculiar angular momentum. When you analyze the angular the angular distributions, you find that the D5 can be populated at very different energies, experimentally. These are the experimental dots. Of course, there is one state that is populated much more than the others. But in this case, is the reaction in the other way around. You send a proton, so a neutron jumps into the proton, creating the deuteron, and you end up with a 119 thing. And in this case, you have, as I was saying, you populate very much one of the states, that one at 0.09 MeV. But with something order of magnitude smaller, maybe not so much, a factor of 5. So you also populate this other state with 1.3 MeV. With then with an order of magnitude smaller in intensity, you populate an state at 0.9 MeV. And well, here you have other different states being populated even less, but still can be measured at 0.7 and 0.6 MeV. Well, this is the so-called fragmentation. And the fragmentation has to do with partition coupling, because you have to solve an extended matrix problem. You don't obtain just one eigenvalues in BCS, you obtain many, and these many eigenvalues, each of them has an X amplitude, as a quasi-particle amplitude. They are plotted here. Well, this is the experiment, sorry, this is the experiment, the amplitudes you obtain in the experiment. In particular, this would correspond to the analysis of this data. You have similar data for the other reaction that are plotted here. And here, again, the same data. Don't look at this side. Here you have the same data, okay, but in this case compared to experiment. And as you can see, in the experiment, we are obtaining a fragmentation that, in the case of this special orbital, is observed experimentally. Not exactly at the same energies, not exactly with the same amplitude, but with a very, very similar structure as the partition coupling calculation. So it's a nice example in which we see that partition coupling is acting in this superfluid nucleus. Well, let me go back and flash what happens with multiplet. As I told you, the multiplet is a kind of a special signal of the partition coupling. And well, just as I was showing you the last lesson, we can calculate this for contribution to the to the splitting, and in this case is a is a 1, 2, 3 is a pentuplet, quintuplet, sorry, it's a quintuplet, and here you have the experimental energies of the quintuplet, and here you have the angular momenta, and well, in this side you find the result of the partition coupling. That you could say, okay, you are using a partition coupling that is okay, has the right strength, you can be tranquil in this sense. But this nucleus, or better to say this family of nuclei, give us an even better nu. Because if you do the same with the neighbor nuclei, there is a very special behavior of this element of the multiplet, which has angular momenta 11½ minus 1. And this behavior is a specific signal of diagrams in which you have to recouple angular momenta. There is a 6J, this is a quite technical point, but just let me flash that this is a very, very specific behavior that appears when you move along the isotope change. As you put more and more neutrons, and you increase the mass number, the occupation factors change smoothly, but most of the elements of the multiplet just keep doing more or less the same splitting. So they split exactly the same for every isotope, except this special J minus 1 angular momentum coupling. And nicely, very nicely, the experiment show this signature. So you have a very, very good way of checking whether the elements of your calculation and your description is sound, physically sound. Well, this is more or less what I was saying before. And well, you can go to other different observables, like the two-particle transfer. In this case, it was calculated by DWBA. And it depends very much on the gap. You can do a naive, today we can say so, a naive BCS calculation with a very simple pairing interaction, and in such a way that you reproduce the experimental pairing gap, and you obtain, well, a cross-section that is not far from the experiment. Or you can only include the argon interaction. You say, well, I don't know nothing about partition coupling, I put just the argon interaction, and you obtain something, well, not far from the experiment, at least in the error bars. And when you perform the full NG calculation, is here for the nuclear field theory calculation, meaning you include the argon interaction and the partition coupling, you obtain something which is also in rather good agreement with data. So one could say that this observable is not very sensitive to fragmentation, because you don't have fragmentation here, you don't have fragmentation here. Well, it's an open question whether when the experimental error bars become smaller, some sensitivity could be obtained also for this observable. But by now, it's somewhat democratic for, let's say, for these three different ways of calculating. Well, and this is just summarizing of all the experiments, all of the observables that we have been analyzing, and these are, well, the deviation, the systematic, the errors, let's say, that we obtain. These errors are obtained with the Lyon-4 scheme interaction. This is with a little bit optimized scheme interaction, but as I told you, we have there is not a single scheme in the market that had been fitted in order to leave room to the partition coupling. So why should we take for granted that slide 4 is the best? So we wanted to study whether we could find an optimal set of levels. Since nobody can tell us what are the real bare single particle levels, we took the freedom of changing the single particle energies and tried to optimize the situation, the comparison with the experiment. And in this way, we could get somewhat better average agreements and smaller errors, but not that much. So this gives us some more confidence on this scheme interaction that was not in principle produced for this purpose, but that every time that we use it, gives us a good basis for the calculation. Well, B2 are the quadrupole transitions that I have skipped, but well, I can show you. I just can't flash. If you go to the experiment to the 319, you in the low energy spectra you find the quadrupole transition between different states. In principle, the 119 nucleus, all these are of a configuration in which a neutron is moving in an excited state and then going to the more bound single particle, quasi-particle states as the one you find here. If you did just a BCS calculation or a Hartree-Fock-Bogoliubov calculation, all this number would be 0, because you have neutrons, quasi-particle neutrons, and neutrons are not charged particles. So there would be no electric transition from the neutron quasi-particles to the other neutron quasi-particles. But due to the mixing of the neutron with the phonon, and the phonon is the core vibration and includes also protons, due to this mixing, there is some amplitude, some proton amplitude in each of the quasi-particles. And the mix, this mixing allows or gives rise to the possibility of a quadrupole transition among them. These are the experiment, the number, these are the theoretical numbers. Again, the comparison is not, let's say, perfect in the sense that you don't reproduce exactly every number, but the main aspect, which are strong, which are weak transition, etc., are reproduced in a, let's say, reasonable way. For example, look here. Maybe, I hope, the strong one here is from the 3/2, and if you take the 3/2 here, in fact, it's stronger. So you obtain a reasonable description of the strongness and weakness of the different transitions, and you get also again confidence on the way you are calculating the configuration mixing, in this case with the particle and phonon intermediate states. Well, this is just an example in a nucleus, in a superfluid nucleus, of all the observables that you can get, and I hope you can get the feeling of how this partition works in a real case. And now I stop for 5 minutes, and then I will come back with a different application, namely to states lying in the continuum, or at least coupling strongly to the continuum, as in the halo states, as in the halo nuclei, sorry. Comincio? Aspetto? Okay, so let's go now to the case of nuclei in which the coupling to continuum states are important. In particular, this is rather relevant in the study of the structure of halo nuclei. So by now, we were always thinking well, for protons and neutrons, and some Fermi energy, and the levels. And all the examples I have shown to you until now are referring to levels with negative energy, meaning they are bound. But if you have nuclei where you have, as in the case of neutron-rich nuclei, you have almost all the levels of neutrons occupied, the states of the continuum are very close. For well-bound nuclei, you could say, well, the continuum, if this is very deep, the Fermi energy is here, and the continuum is here, well, you can say that you have so many levels here, and the differential energy is so large that the coupling to the continuum can be, in principle, forgotten. But this is exactly the opposite situation in the case of neutron-rich nuclei. Or also in the case of proton-rich nuclei. If you have proton-rich nuclei, the same thing happens to the proton side. Well, you have here the Coulomb barrier that helps a little to maybe to think in different types of states, but still the coupling to the continuum through the tunneling is important for many purposes. So in principle, in both sides, proton and neutron-rich nuclei need to handle the question of the continuum. Well, you will get a somewhat surprised how easy it is to implement the continuum in the scheme that we have already seen. We have been looking at the basic ingredient of all this type of calculation, which is the partition coupling. And remember that this has a structure in which you have the wave function of the radial wave function of the initial particle, the radial part of the surface deformation, and the intensity was related with the 0-point amplitude of the phonon. And then you have some Clebsch-Gordan that, well, you can put it if you want in order to modulate the different matrix elements properly. And these are the ingredients you have. Well, I also told you that if you don't want to use the collective model by Borel-Mottelson, you can substitute here the RPA corresponding amplitude. Which is similar. similar in the sense that the UDR is something of the sort, around the radius of the nucleus. Is the derivative of the potential. Sorry, is the derivative of the potential. So it gets a maximum around the Fermi energy. And if you perform RPA calculations, well, you don't obtain exactly this function, but you obtain usually something similar for the surface forms, for the low lines. So in any case, I put UDR, but remember that you can also put RPA. Okay. Well, in principle, there is nothing that forbids the use of exactly this expression, with this or with that, for levels in the continuum. The way in which the problem of the continuum is that you have an infinite number of states. That's why it's called continuum. But the usual way of attacking this problem is to make some discretization, some bins of energy, and then you proceed little by little, reducing the width of these bins in energy, and try to see if your calculation converge. Well, this is exactly what we do. The way in which we perform the discretization is by a very simple method, which is put perfectly reflecting walls at a radius that we call a box radius. And in this way, well, naturally, when you solve the Schrödinger equation with the Booth's action or with the Hartree-Fock together with these perfectly reflecting walls, with the usual boundary condition, you obtain here again a discretized spectra, much more dense because it's a large box. This is not in scale. Usually we use boxes of 40, 50, 60, sometimes even 70 Fermi. And we study the convergence of the different calculations as a function of the box radius, and we analyze if we can extract meaningful information from these calculations. And in this way, the only thing that happens in our partition coupling is that we cannot simply think in one, let's say, d5 half state around the Fermi energy. We will have the d5 half here, but many other d5 halves in the continuum or in the discretized continuum. So when we establish the partition coupling, our basis cannot be constructed only with one of these states, but we have to include many. The first, also the second, the third, and so on. So our single particle basis, instead of only one single particle, will be composed of many. Most of them, or some of them, in the continuum, or in the discretized continuum. Okay. So in our partition coupling matrix, what in principle was just one column, now are n columns, and the same for the files. Sorry, for the rows. Okay, so in the Booth-Saxon approximation or in the Hartree-Fock approximation, all these states are orthogonal. They have some single particle energy that we would call E1, E2, E3, En. But now we know that all of them, because of the particle relation coupling, can couple two particle phonon configurations. Here, of course, now we will have also much more than before, particle Hall configuration, particle phonon configuration, because we have many particles in the discretized continuum. But the thing is conceptually exactly the same. These are so now for every single particle state, each of them will have a matrix element that will be calculated exactly with the same expression we had before. Of course, when you change from the first to the second, you have to change the radial wave function, and this will give rise to a different number. So this matrix is not a uniform one, but contains all the details of the radial dependence of the single particle states bound or in the quasi or in the discretized continuum. Okay? So here you have a matrix of particle vibration coupling matrix elements, all of them calculated with the same. Okay. And in this way, we have a straight ahead generalization of what we did before. Of course, you can include particle phonon configurations that give rise to the self-energy of this kind. The fact that now we have many single particle states means that in these diagrams, when you put this perturbatively in the other side, in these diagrams, the initial and the final D5 have not need to be the same. For example, this could be the first one, and here the second. Okay, each one with his own vertex, calculated in this way. So you can reduce all this big matrix to the self-energy that in this case is a self-energy matrix, because it can couple different states with different number of nodes in the single particle basis. So in this case, the self-energy would have two indices that before we don't talk about, but now are needed to specify exactly which of the matrix of the particles are getting coupled. And this can be done with this contribution and with the other, with the Pauli principle one. Here also you can go from one number of nodes a single particle state, different number of nodes a single particle through the Pauli principle correcting diagram, and well, each one with his own vertex, again calculated as usually with this equation here, with this little formula. And when you sum all of them, I mean both of them, you sum up both of them for each combination of number of nodes, you obtain a self-energy matrix containing both effects, and which, remember, depends on the energy denominator, which is meaning that this is an energy dependent. This is an energy dependent self-energy matrix in this case. Okay, so what we solve is precisely this self-energy problem, namely, now that we have constructed the self-energy, we only have the single particle basis. Number 1, number 2, number 3, n. And now we proceed to diagonalizing this matrix, where we have, of course, the Hartree-Fock original energies, but now we add, in this case, the 1, self-energy, in this case, the 1, 2, the 1, 3, 1n, and so forth. The 2, 2, the 2, 3, and so. This is an eigenvalue problem with matrix elements that are energy dependent, because each of these functions is an energy dependent one. And we have the different amplitudes. And solving this problem with the energy dependent here, we obtain new single particle energies, okay, and new single particle states. Okay, so suppose that we have one let us look to the first one. This will have an associated eigenvector, the one of the first eigenvalue. Okay. And well, from this amplitude, you can construct the new wave function of the first eigenvalue you obtain just by summing, by the sum of the different amplitudes with the original Booth-Saxon or Hartree-Fock wave functions. And in this case, well, you obtain a new radial wave function that has the peculiarity that in the asymptotic part, if you plot the wave function in a logarithmic scale, well, you know that the final part of the wave function of a single particle wave function has to decay according to the exponential law, in which k is if it is bound. I'm supposing here it is bound, okay? Since you have changed the single particle energies, these tails must also change. Suppose that you now get a state that is more bound. Well, then you will need to to get a tail that is going down faster. And for giving rise to this change on the shape of a wave function, you need this kind of linear combinations. Okay. This is also true for well-bound systems, not only for weakly bound as hollow nuclei, but in the well-bound nuclei, the change you obtain in the energy are relatively small. So we didn't mention this before. But if you are in a state which is already close to the threshold and you obtain an increasing in binding energy, this change can be very sizable. And in this case, the coupling to continue is completely unavoidable. Well, one thing that is to be remarked is that this is an energy-dependent eigenvalue problem, namely that the matrix itself is energy-dependent. This gives rise to much more eigenvalues than the dimensions of the matrix. If you have n times n matrix, in principle, in an energy-independent eigenvalue problem, you would obtain n eigenvalues. Here, the number is much more. This is because you have the fragmentation. Remember that this self-energy is related to the coupling to other configurations that are not explicitly present in this representation. So remember that behind this eigenvector, we also have particle phonon configurations. Okay. Well, once you have found an eigenvalue that that verifies this eigenvalue energy-dependent problem, and you have obtained this eigenvector, you can proceed by straight-ahead techniques that, well, can be easily deduced from the things that we have already seen, but that I don't want to now to say explicitly, but just to mention, you can get the amplitudes that we were saying, the C amplitudes, or we can obtain the corresponding to the holes, the D amplitudes, that we call D amplitudes. So we can also get these amplitudes, and as I told you, as I was telling you, has to do with the fact that when you construct the self-energy that we have used here, behind you have the coupling to this other configuration. So to some extent, part of the time your state is living in this configuration and you have some amplitude. Okay? And this happens with every eigenstate that you obtain from this eigenvalue problem. Okay, this is very schematically how we treat the continuum. Then I will give you some other details about the analysis of the result in the specific case of the application I will show you later. And so now let me go ahead and look to the application of the one of the most let's say studied nucleus in literature, which is beryllium-11. Although the discovery of hollow nuclei was done by means of this lithium-11. Lithium-11 has 3 protons and 8 neutrons. Lithium-9 was known from long time before, but lithium-10 is not bound, cannot be produced for almost any time in the laboratory, but lithium-11 was observed in the detectors. So it has a long enough life to be detected, and the first analysis were concerning the cross-section of production of the lithium-11. And from this cross-section for production of lithium-11, it was realized that lithium-11 has a radius which is much larger than that of the lithium-9 core. Here you have some numbers. The lithium-11 matter radius is 3.20, well, there are several experiments, but it's around 3.3, while that of lithium-9 is 2.3. Okay, so this is an abrupt change, and to realize how much abrupt it is here compared on a scale with the size of lead 208. So this would be lithium-9, which is again, no, this is not lithium, this is beryllium. So this is lithium-9, then the radius corresponding to lithium-11, and here, well, you can see that this increase in the size of the nucleus brings you to a size that is not as large as a lead nucleus, but well, it's something that is in between. So showing that these nuclei show what is called since then a hollow structure. This is a large structure, but with a very low density because it contains only 2 neutrons in the case of lithium-11. So it's kind of hollow, and this is the name that has been kept until today. Well, there have been a number of hollow nuclei discovered since the first one, lithium-11, and one of them is, as I told you, beryllium-11. Beryllium-11 is a one hollow neutron, so it's just one neutron in the halo. It's even more hollow-like in a way than lithium, because lithium. So it's just one neutron in a very external. This is an exaggerated way of drawing, but it's just one neutron in an orbital which is very out of the core. And, well, in principle, the fact that the orbital is very far or very extended in space has to do with the tail I showed you before. If you have a weakly bound nucleus, a weakly bound single particle state, the decay of the tail will be very small. If you approach to 0, this k approach to 0. So you can, in fact, expect that a lot of the wave function is outside the nucleus. Maybe the nucleus is somewhat here. Okay? This is logarithmic, of course. So it's not surprising that you obtain, let's say, very extended structures as you go to very rich neutrons, because your neutron levels are approaching to 0. Here is the scheme of neutrons. Well, this is carbon-13. Carbon-13 would be a neutron, 6 protons, 6 neutrons plus. If you take out 2 of these neutrons, you go to beryllium-11. If you take out only 1 of these protons, you have boron-12. So you have the so-called isoton chain, in which an nuclei with decreasing number of protons, you can see what happened to the neutron levels. And of course, what happened is that the neutrons feel less and less bound, because neutrons like to be surrounded by protons. So if you start to eliminate protons, the level of the neutrons start to grow in energy. This happens with the P1 half, the S1 half, also with the D5 half, which is not shown here. This is a Hartree-Fock calculation, a standard Hartree-Fock calculation. And, well, in this way, you can explain the appearance of the halo structures in a simple way. But the beryllium has a peculiarity which has been called for a long time parity inversion problem, because the ground state of beryllium, which would be putting here a neutron, is not 1/2 minus, as you would expect from this scheme, but instead is 1/2 plus. And on the contrary, the first excited state of beryllium-11, instead of being the 1/2 plus, is the 1/2 minus. In this sense, it is called the parity inversion. So, very schematically, the situation, experimental situation in beryllium-11 is that the orbital 1/2, the state 1/2 plus, the positive parity state, is lower by a small amount, because we are talking here about very small binding energy. This is a binding energy of about 500 kV. the binding energy of the other states is about 200 kV. But still, they are in the, let's say, wrong order with respect to the Hartree-Fock. It's not only the order, but the fact that, as you can see here, the distance between the P and the S in many Hartree-Fock, other Hartree-Fock are less drastic than this one, but would be the other way around for a sizable amount. Not only 100 kV or 200 kV or even 1 MeV. One would say, well, okay, I cannot reproduce the detail, but many Hartree-Fock calculations are showing sizable gaps between the P and the S. So it was a question why these two levels got the other way around in the experimental data. Well, this was an opportunity for partition coupling, because we know that partition coupling moves levels around. So this was a clear opportunity. Of course, partition coupling is not that appears spontaneously in the beryllium-11. Should appear also in carbon-13, oxygen, etc., etc. I will show you before calculation for beryllium-11, but then we will see that this is a progressive behavior of the levels when you move in the isotope chain. This is the experimental situation. Okay, as I told you, in beryllium-11, you already have the parity inversion already present, but this is something that is getting developed through the isotope change. The is just an extrapolation. There is a great debate nowadays about the exact position of the resonances, but this is just a cartoon. These are real experimental numbers. This is just an extrapolation. Well, and the idea, as I was saying, is here we have an opportunity to check whether we get some information and some lesson from the partition. The ingredients of the calculation are, as usual, the same always. We use, in this case, we use experimental quadrupole state properties, the deformation, the energy. We use a Saxon-Woods plus a spin orbit for generating the single particle states, and then calculate the self-energies. In this, we have performed different calculations. The results I will show you contain only the 2+ coupling. The coupling to other modes, although they are not negligible completely, are very little meaningful for this case. So let's concentrate, and this is the result I will show you on the effect of the quadrupole of the coupling to the quadrupole state. And when one does this, one obtains a correction to the levels that is as the one you see here. You see here, in fact, the P1/2 in the Woods-Saxon at a sizable distance from the S. The D is already very large. And when you apply the self-energy with the parameters that we extracted from the experiment, in particular for the quadrupole state, we obtain immediately the parity inversion. Why is that? Why is this level going up and this level going down? Well, it's because the very specific situation in this kind of nuclei where very few, only 2 or 3 levels are available for the couplings. If you couple to the 2+ and you have an S1/2, you need a positive parity state here to develop the diagram. In this case, you have one, which is the D5/2. If you want to develop this diagram for the P, here you would need something like a P3/2. But the D5/2 although in the continuum is a resonant state, while there are not single particle resonant states of this character in the continuum. So these diagrams are very hindered by the fact that the continuum is coupled much weaker than the resonant states. On the other hand, for having this self-energy in the S, you would need here a whole state of positive parity. The only whole state of positive parity is the S1/2, but it's very deep in energies, and moreover, it's not enough for the angular momentum coupling to give any result. So this is exactly 0 in this case. And instead, for the P1/2, you have just below the Fermi energy, you have the P3/2, as I showed you before. And this, remember, this state is systematically giving lowering of the energy, and this is systematically giving an increase of, and this is what we observe here. Okay. There are other details about the resonant D5/2. We had to go to higher orders in the diagrammatic expansion, but well, I don't have time today. And in this way, we could, with a single particle, with one single particle potential, we could generate single particle energy levels, going from the Booth-Saxon to levels that are essentially, or which are very, very close to experimental. And as I told you before, from the amplitudes we obtain the wave functions, and from the wave function we can do calculation of one particle transfer reactions that are in reasonable agreement with data. And just let me mention the sorry, the possibility of populating the 2+, the phonon, through the one particle reaction, because this is a very specific signal in our scheme of the mixing with particle phonon.
I think it would be better if you download the Excel lecture. So maybe you can do some time to that in the afternoon, because it's, I think it's
But could I have 2 minutes?
Yeah, of course.
Yeah, I just. So, as I was saying, this is a very specific signal of the partition coupling, because, as I was saying you before, our parity inversion is strongly or is due to this kind of processes, in particular for the S1/2 through the D5/2, meaning that the 1/2 plus state part of the time is living in this configuration. So if the proton in the reactions or arrives just when the beryllium-11 is performing this configuration and takes the neutron precisely at this time, this is a way of speaking, but it's quite realistic. What would be, well, this will scatter and disappear. What will be behind, what is remaining in the beryllium, is a beryllium-10, but excited in the 2+ state. And this should occur with the amplitude square to get a probability of this component, namely the one that we obtained from the diagonalization. This component in our calculation is about 0.7. That is precisely what the analysis of the data by the people that performed the experiment obtained. They were having some kind of problem an exact determination of the number, but they did good work in the sense that it coincides very much with the nuclear field theory analysis, and they got essentially the same number. So this is a very nice confirmation of the mechanism that is behind the description of this halonuclei. Well, okay, I stop here. Now it's time to break, and this afternoon I will give some more general aspects of this kind of calculations and try to give a broad picture of how this kind of calculations are inserted in the market, let's say in the usual things that are done in literature. Okay, thank you.